So let's talk about the variance. Let's talk about the contemporaneous variance first. So we'll make the substitution for ut squared. So the first parentheses is ut times ut, where I expanded the sum, at least the first two terms. And then we can multiply out the two sums. So we get epsilon t squared. We get rho squared times epsilon t minus 1 squared plus rho to the fourth times epsilon t minus 2. And then we get all kinds of cross products. When you were in, I don't know, 7th or 8th grade, you had to do all these expansions with the quadratic formula. So we have all these cross terms, and what's the significance of the cross terms? Well, the significance of the cross terms is that the time subscripts don't match on the epsilons. And we said that as far as the white noise is concerned, there is no correlation between periods. So all the cross terms vanish in expectation, and we're left with all the epsilon squareds, which is common to every single term in the sum. So if we factor out the expected value of the epsilon squared, we end up with sigma epsilon squared times the series, 1 plus rho squared plus rho fourth, so on and so forth. And probably in the first semester of calculus you did these things, and now is when we reap the fruits of having assumed that rho in absolute value is strictly less than 1, because that series is 1 over 1 minus rho squared. So the expected value of ut squared is sigma epsilon squared times 1 over 1 minus rho squared. So let's look at the instance where we look at today's disturbance times yesterday's disturbance and take its expected value. So substituting away from ut and ut minus 1, we're going to look at the expected value of that product. So I put in some parentheses in order to group things so that you can keep track of the multiplication a little bit more easily. We have epsilon t plus rho times big ut minus 1, which is the same as what we have over here. So the expected value of ut times ut minus 1 can be broken into epsilon plus rho times ut minus 1 times ut minus 1. We already know how to take care of the cross products. Epsilon t times any term here, the time subscripts don't match, and in expectation they're going to be 0. So we only need to worry about rho times the part in parentheses times the other part in parentheses. We have open, 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 3 opens, 2 closes, we're down to 1 open. Open, we're back up to 2 opens, and then close, close, so they're balanced. Basically all we need to look at is that product, which is rho times ut minus 1 squared. Well, whatever was true for the expected value of ut squared has got to be the same for ut minus 1 squared. So we end up with, when there's a 1 period offset between the two disturbances, we end up with rho times sigma squared epsilon times 1 over 1 minus rho squared. Let's go ahead one more step to see whether or not that there's any regularity. Let's look at ut times ut minus 2. The regularity again does emerge in their product. You group things so that you end up with epsilon t plus rho times epsilon t minus 1 plus rho squared times ut minus 2, all multiplied times ut minus 2. Wherever the time scripts don't match, in expectation you get a 0. Where they do match, you get a sigma squared epsilon. But now you have a rho squared, because there's a 2 period offset. You have a rho squared times the expected value of ut minus 2 squared. And we know what that is. Sigma squared epsilon over 1 minus rho squared. So at the end of the day, we have sigma squared times sigma epsilon over 1 minus rho squared. So there's a pattern that's beginning to emerge. If we took the time to go back and look at the expected value of ut times ut minus 3, we'd have rho cubed times sigma epsilon squared over 1 minus rho squared, and so on and so forth. The good news is that if big U, here, if big U is the column vector of U1, U2, U3 through U big T, and U transpose is the row vector, U1 through U big T, we get a big T by big T matrix, which is the error, and take expectations, we get a big T by big T matrix, which is the error covariance matrix, that's very highly structured. It has sigma squared epsilon over 1 minus rho squared times this very special pattern matrix, method matrix. So we have ones down the main diagonal. The first off diagonal is all rho. The next off diagonal is rho squared. And you keep increasing the power on the rows until you get all the way out to the row 1 column big T position where you have rho to the T minus 1. And it's symmetric because after all it's covariance matrix. So below the main diagonal you get the same kind of pattern matrix.